Hey guys, David here. I'm going to explain to you everything you need to know about Chapter 4. Alright, first up we got metallic bonding. Metallic bonding is unique in that all the atoms sort of clump together and they share their electrons. In this diagram I drew here, I have a bunch of gold atoms. They're all grouped together and the electrons are scattered randomly throughout the atom. They are non-localized, which is just another way of saying that each individual atom doesn't hold on to its electrons. They share them in a giant pool. Because of this, it has two important properties that you need to know. It is conductive, meaning that electricity can pass through it because the electrons can move freely. And it's also malleable because no bonds will be broken if, say, the gold atoms are shifted one way or another. Another thing you need to know is that metals form two alloys, substitutional alloys. I think I spelled that wrong. And interstitial alloys. Substitutional alloys have similar functions to their pure metal counterparts. They are simply the same, except certain atoms of one element are replaced by a metal of a similar size. Interstitial alloys, on the other hand, are made up of two different metals of different sizes, where one metal is interspliced between the atoms of another. And because of this, there are more atoms and less space, and it is a dense compound. Moving on to ionic bonding. Ions bond like this. These are two diagrams of ions in their solid states. Here we have a 1-to-1 ratio. Here we have a 1-to-2 ratio. So something you'll notice about the ions is that you don't see the dots. That's because their electrons are localized. Those ions hold on tightly to their electrons. Another thing you may notice is that they have this sort of pattern of negative, positive, negative, positive. In other words, you can't really shift the row over one atom without having the two negatives get closer together, two positives get closer together. And as a result of that, the ions are not very malleable. They will break if you try to put too much force on them. And they also are not conductive in the solid state. However, when dissolved or when in the liquid form, they are able to conduct electricity. It's a little difficult to draw. However, you just need to know that when ions are in the liquid or aqueous state, they are conductive, but when they're solids, they aren't. All right, ions are formed in a 3-step process. The first step is the metal gives up its electrons. This process is endothermic, which means you need to put energy into it. The next step is the nonmetal gains the electrons. This process is exothermic. It happens on its own accord, and it releases energy, little energy. Then the third step is the nuclei come together. This is the biggest energy booster of the process, and this releases lots of energy. When ions form, they need to form in the ratio of the ions that they make. So, for example, when calcium and chloride come together, calcium has 2 extra valence electrons, while chlorine needs 1 more to complete its octet. For every representative particle, you need 1 calcium and 2 chloride in order to make your molecule. Moving on to how you name your ions, you just say the name of the positive followed by the name of the negative. And when your positive is a transition metal, you write the Roman numeral of its charge. For example, if you're doing iron, you would say Fe3+, you do 3 Roman numerals. For CaCl2, calcium chloride, because this is calcium, that's chloride. Cool. We'll get to this later. This is about naming covalent compounds. All right, covalent bonding. Basically, atoms prefer to have full octets. They prefer to have 8 valence electrons. Covalent bonds look something like this. These little lines, they represent 2 electrons. So this oxygen atom in the middle is very happy because it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. An important aspect of covalent bonding is the shape of the molecules as the state changes. Basically, the molecules spread out more as the temperature increases and the state of matter changes. Over here we have solid HBr, very close together, liquid, slightly more spread apart, gas, completely disassociated. We have the distance between the nuclei versus the potential energy of both of them coming together. If they get too close, they will repel each other. That's why the potential energy becomes positive over here. And if they get close, other than that, they want to get closer together. You need to know that this distance right here, that is the length of the bond, and this is the amount of energy that bond has. It's the amount of energy it takes to break that bond. Back to the naming of covalent compounds, you want to say the names of each element with the prefix corresponding to the number of atoms in it per molecule of that element. So here we have sulfur dioxide and phosphorus pentafluoride. So as you can see, there's no mono prefix in front of sulfur nor phosphorus. That's because you don't use the prefix mono for the first element. But then you see the dioxide because there's 2 oxygen, and pentafluoride because there are 5 phosphorus. Alright, so now you can pause the video if you want to try out these problems for yourself. I'm going to do each of these problems that I've created, and then I will explain why I got each answer. There are actually 2 pages of problems, so after I do this one and explain it, I will move on to the next page. Okay, so pause the video right now if you want to try it. All right. This is metallic. This is nitrogen trifluoride. This is carbon monoxide. This is dihydrogen oxide. This is iron oxide. Three representative particles of BAF2 would look like this. This is one. I'll box them off so that you know which is each. And the conductive compounds here would be NaCl, Fe, and Au solid. Okay. So, the first one, we know that that is metallic because you can see all of the metal atoms are grouped together. You don't really see any bonds. You don't see any charges. So, you know that it can't be ionic. It probably would have looked better if there were electrons. But because they're all grouped together like that and you don't see any bonds, you don't see any charges, you know that has to be metallic. Moving on to the naming. NF3. So that's 1 nitrogen and 3 fluorine. So you know that you don't use a prefix when there's only 1 element in a covalent compound. So you just have nitrogen for the first element. And then the prefix for fluoride when there's 3 of them is tri. So it's nitrogen trifluoride. Carbon monoxide. Again, it's 1 and 1, so you don't use monocarbon because there's only one carbon, but you do use it for the second one, making it monoxide. Here we do finally have a prefix to the first one. We have dihydrogen oxide. Most people call this water. However, its chemically correct name is dihydrogen oxide because there are 2 hydrogens and only 1 oxygen. Here I tried to trick you with an ionic compound versus the other covalent ones. Here, iron does form a 3 ion, so you need to put the 3 in Roman numerals. Now, I know some of you might be thinking why I didn't put diiron trioxide because there's 2 iron and 3 oxygen, but the reason I didn't do that is because Fe2O3 is ionic, and for ionic compounds, you do not use the prefixes, and that is to distinguish between covalent and ionic compounds. So make sure you include this Roman numeral because iron is a transition metal, which means it has multiple different charges. Moving down here, 1 and 2. So barium has a charge of 2+, where fluorine has a charge of -. So you need to have, let's say 1-. You need to have 2 fluorines for every 1 barium. This is pretty straightforward. It's just something conceptually you need to know. You need to just box them off like that. Yeah, you want to keep negatives away from each other. You want to keep positives away from each other. Conductive compounds, NaCl. This is an aqueous ion. It conducts FeS. This is a metallic substance. All metallic substances conduct. AgCl3. AgCl3 is an ionic compound, so it conducts in its liquid and aqueous states. You might not have been able to see it, but there is a solid here, and ionic compounds are not conductive in their solid states, so this would not conduct electricity. CH4, that is a molecular covalent substance, and that does not conduct either. AUS, another metallic. Yeah. Covalent substances do not conduct, and neither do ionic compounds when they're in the solid states. But it's an important distinction between solid, aqueous, and liquid ionic compounds. You should know that for the test. All right, second and final page. Please take a second to pause the video if you want to try this for yourself, and then I will go on and complete it and explain. All right. The ion formed by magnesium and iodine is Mgi2. The alloy presented here is a interstitial alloy. The 3 steps of ionic bond formations are ionization energy, which I'll abbreviate to IE, electron affinity, and lattice energy. This is endothermic, this is exothermic, this is also exothermic. Bond length is this, and it is this much on the x-axis. Okay, now for explaining. Magnesium forms a 2+ ion. Iodine forms a negative ion. So therefore, you need 2 iodine for every 1 magnesium, meaning you get Mgi2. What type of alloy? So here you have a big metal, and then in between it, smaller metals of a different size. So when the 2 metal atoms are not the same size, you know that it is a interstitial alloy, because a substitutional alloy would have 2 metals of similar sizes, kind of replacing the gaps between metals of the same size. But when it's much smaller like that, they fit in between the gaps of the bigger atoms. An interstitial alloy like this would be more dense than the pure metal. The 3 steps of ionic bond formations, this is pretty straightforward. You should know these names. I did not, and I remember I got some questions wrong in the tests. Ionization energy, electron affinity, and lattice energy. If you can't remember that, then just remember that the first step is endothermic. That's when the electron is released from the nonmetal. Electron affinity, that is exothermic. That's when it gets attracted to the nonmetal. And lattice energy, the nuclei come together. This is the big exothermic step right here. Bond length, don't forget about this diagram. This thing right here, like I labeled, that is the bond energy. And then, sorry, that is the bond length. And then, like this X length. And then the bond energy would be this down here. This graph is important to know going forward. You won't really use it, but you will get tested on it. So just remember bond energy, bond length. All right, I hope you understand this chapter. I wish you all luck on your test, and Tigers forever. Good luck with AP Chem, guys. Great course. Toodles.